Okay, assignment 4. Am I recording? I am recording. Cool. Fold, unfold. Obviously I'm using a different microphone because I've moved him back with my father. So, consider the following data type of polymorphic leaf trees containing a label on the leaves. So it's basically like a normal binary tree, except that it doesn't have any labels on the nodes themselves, only at the leaves, which is fine. It's a bit easier, I think. Define the base functor. The base functor represents one layer of the type. I like that they give this as a hint, because you should know this yourself, but it's nice. This type together with the corresponding instance of class functor. Okay, sure. So we have to define a data type. Right, so defining this data type, you've done many times, and it's also incredibly easy. It consists of, basically maybe 3 steps, right? So step 1 is capitalizing everything. I'm just going to do it by the steps to make it easier. We'll capitalize everything that's not a variable, right? So this would be single, lm, or join. And then here we'd have tree lm, which I'd like to paste as well. Okay, so that was step 1. Then step 2 is removing the recursion. So there's 2 recursions here. So here we say that a tree of lm contains 2 trees. That's typical definition of recursion. Remove them, just remove them, put something else in place. Let's call them int. Well, int is maybe a bit confusing because int is already something else, but I'm thinking of a word to represent an intermediate result, because with a base functor, that's what it represents usually. Let's say res for result. That's step 2. And step 3 is now fixing the type, because what we've done is we have introduced a new variable, which is res, which is not on the left side of the equal sign, which is not allowed. So let's fix that, and there we go. That's how you define the data type for a base functor. And from this, defining the functor instance is quite easy. Whoops, let's fix my spelling. Instance functor. We'll leave this open for now, and then we have an fmap of f. Sure. So the thing is, for a functor, defining the functor is not something you really have to think about. It's about following steps, especially when it comes to the simple assignments that will be given on the exam. So for a functor, knowing what it says here on the 3 dots is trivial. You just take the data type that you want to implement the functor for and leave out the last last argument, and that's it. So they know what it's supposed to be. Well, we want to define the functor for tree, for this tree, capital tree, right? So that's trivially easy. Just write tree lm, don't write the last argument, there you go. And this also gives us immediately what we want to fmap on. The function we get that we want to map on this data structure, hence the name fmap, is the argument that we left out in our definition here on line 6. Right? So that's how we know what to apply the function for, which immediately brings us to the first the case. Pattern match, I guess. So we pattern match on single of lm. Now, I said before, the data type that we want to perform our function f on is the res, right? But it's not found in single, which means that here we don't care about f, and we can simply return lm, because keep in mind that functor should not modify the structure of your data structure. Nice. Okay, well, we can copy this. This time we do need f, of course, for the join. Let's call them R1 and R2. You can call them RL and RR or something, or LR. This works too. So this time, now we do have the data structure that we want to apply the function on. So f R1 and f R2. still not changing the structure of our tree, but we do perform the function. So this should be it. Let's see if I fucked up. Don't go too far. Okay, so the data type seems identical. It is actually identical. Nice. So res, you can always use res, I guess. Then you should always get something that looks very good. And then we have our fmap, or functor, sorry. Yep, that looks identical as well, except that I'm using R1 and they use L now. Cool. The correspondence between the original nice, between the original recursive type and the base functor should be given in an instance of class base. Very true, because once we have this idea is that we define that we will later on be allowed to define a function for a single layer of our data structure, but we still need to give the compiler or the program some way of converting from our non-recursive version to a recursive version. Fortunately for us, this is, well, I mean, fortunately for us, this is something the compiler can do for us, but in our case we have to do it ourselves. But the fact that the compiler can do it for us says that it's quite easy. And again, it's just following a few steps. So let's do that. Oops. Oh, they give you the class here, which is nice. So again, what do we want to have here? It's very similar to the function. In fact, you should keep in mind that it's the same. If you follow the steps that I mentioned earlier here, well, actually no, it should always be the same. There we go. Keep in mind that you shouldn't write this here because that's only for the class definition. All right. So we have to tie the recursive knot first, which is to say what the recursive version of our tree elem is. Right, in this case that will be tree elem. Okay. I'm actually kind of not sure if this is the right way to write it down, but we'll see later anyway, so it doesn't really matter. And then we need to have an in, which I'm not sure what it says f here. Do we even need that, or should it be like this? Let's do it like this. I feel like that makes more sense. For in, we take the tree, the capital tree, which has as the result, right, the recursive version of the tree. So, for example, I mean, single will still be single of just x, but for the join, you will have here a normal tree. Let's call them T1 and T2 to make sure that we understand that they're trees. So for a single, just go to single. And for join, we just go to join. Because we're taking this base, this capital tree, and we have to output the normal tree. And the opposite is true for out, where we take the recursive function and output a non-recursive function version with where the result is the tree. Right. So I mean, you can also see that here it's written here because we defined rec f as being tree of lm. So that means that the f of the f of rec f, sorry, with the f being tree lm, right? Keep that in mind. We have kind of like curried this lm type, meaning that whatever we give f here is actually the res, right? So that's how I know that this join will have the two trees as children, I guess you could say. So we take the recursive function, which has a single of x, and we output a single of x. And then for the join, it has, oops, that's not the right join. It has just two trees, T1 and T2, which we then just put into T1 and T2. Honestly, making, well, except for what I'm struggling with here, which is the notation here, this is copy-paste work. I really hope I didn't fuck up right now, because that would be embarrassing as hell. Let's look at the solution. So apparently I had to write this here. Let's do that. But other than that, looks good, right? I didn't fuck up anywhere. Nice. I think you have to put this here because it's technically not part of the class, so it doesn't know. That's what I think. But I'm not 100% sure on that. Okay, nice. Next. Use the higher order operations fold and unfold. Okay. So fold is pretty nice. Oh, I'm getting a call. Okay. Yeah, that was a very long call, and I've completely forgotten where it was. I think we were about to implement some functions using fold and unfold, where they've given you a hint in the type, which is that you're not supposed to deal with the tree yourself. I'm pretty sure I was about to say that, and then I got distracted. Yeah, okay, cool. You must not use recursion. Okay. Oops, I hope you didn't see that. Assume that we have a tree labeled with integers. Okay, so a tree of integer. Yeah. Define as function sum that adds up all these integers using fold. Sure. So sum will take a tree of integer and will produce an integer. Now, I said before that the fold doesn't directly deal with the tree of integer, and the same is true for us. We don't need to take it as an argument. We can just return something of this type. Oops. Okay. Yeah, if you want to do it, you can still do this, but I'm gonna leave it out. So we have to use a fold. Well, that's true. We always start with fold. So fold. Let's go back to the type to just keep this in mind. So it takes an f of a, and remember that f of a was a capital tree, and that rec of f is the recursive tree. So we take a capital tree, or just the one 49 is above, and we have to and the intermediate result is of course an integer, because that's what we're trying to get. So, well, there's two ways to do this. We need to make a case distinction either way, right? Because we either have a single or a join, and I think that the answer will probably use something like maybe even a lambda case. I don't know, but I'm not going to use that because I think it's overly complicated. So I'm just going to do this and then use a where. Okay. Well, no, G. G will take. We can actually define this tree of a integer, and it will produce an integer. Because that's exactly what this type is, right? It takes an f. Well, f is tree of lm. So actually, that's probably a good idea to just call this lm. And it produces an integer, which is what we have to return. How can I explain this? All right. So how the types system would realize this is that we have to return an integer here. Here we just have a fold of g. fold of G returns a function recaf to A, which means that this A is this integer, which means that this A is also the integer, which is how I know that this is the type of G. So G takes a single of whatever and returns 1. And it takes a join of 2 integers and returns the sum of them. There we go. That's how you count. Now keep in mind that that the L and the R are the intermediate results. So, you know, we don't have to do any recursion. In fact, we must not use any recursion. Let's check. Oh, I have a lot of... Wait, what? Oh, yeah, I was thinking that this is the exercise, but here it is. Oh no, I'm so stupid. Okay, so what I did here was create a function that counts the number of leaves. But of course we have a tree of integers which has integers on the leaves, so we should instead return the value that is on the leaves. Yeah, stupid. I don't know why why I did that. But it's okay. You know, people make mistakes. In general, the structure is still good, so happy enough with that. Use unfold to define a function grow that creates a tree from a list of values distributing the elements over the binary tree such that the first half of the elements will be stored in the left branch and the second half in the right branch. If necessary, you may assume that this function is always called with the non-empty list. Okay, so again, I think we're gonna have to use non-recursive function. Grow. Let's put the type in there anyway. So there's two functions that are immediately useful. There is, let's open GHCI. There is the div function, which will divide, basically. I was interrupted again. I don't remember. Div, of course, div is just division. It's, I'm pretty sure it's just division. But it's good enough for our purposes. I guess we could also use divide by 2. Let's look at that. Ah, here, it's fractional. So it can produce. No, I'm not sure actually why you use one or the other. Let's use div. Now we have also a function called length, of course. Ingo, which gives us the length of a list, or a length of anything that's foldable. But lists are foldable, so that's fine. So yeah, with that we can easily, divide a list into 2. Which is exactly what we need. In fact, they made it so trivial for us that we don't even have to take out the middle element because of the way the tree is structured. It only has labels at the leaves. So quite trivial. We have to start with an unfold. So where a fold here takes a the non-recursive tree. The unfold takes produces the non-recursive tree. So you can actually see that in the type as well. Here you go. So you just take a some A. In our case, it will be the list of A, and then we produce something of the non-recursive tree of A, which is just tree lm, or tree AA in this, or tree A list of A in our case. And then you get the list of A, and then it gives you the recursive version of our tree. So again, I'm just gonna whoops. Oh, I've been not using I've been using a tiled window manager for so long, for which I use mouse focus. So I'm constantly doing that. I'm moving my mouse over to my terminal. I expect that I can type, but I cannot. Yeah, back to Grow. Actually, I think we can stay with the type of unfold. Okay, so we'll have G here, and then we will have the list of access here, which means that we can also remove it. So let's do that. Then we have a where, and we have a G again. Now, G we can derive here. It takes a list of A, and then produces a tree of A. List of tree of A, list of A. With A being the elements on the list, and list of A being the intermediate results, which is of course the list of A that we still have to divide. Okay. If it's useful, you can assume it's non-empty, but we don't give. Well, let's assume that actually. Yeah. I mean, we can have a pattern match here and just say error, but that's we don't need that. We can assume that this though, which is just a single of x, right? If we have a singleton list or a single element in the list, then we must produce a single from that. I mean, the constructor says so. Then here we have a list that's either empty or has multiple nodes, but we can, like the Simon said, we can assume it's non-empty. So, well, then I suggest that that's not how you do this in Haskell. I am an idiot right now. Let's just use where clauses. I'm so sorry. I've been programming clean for so long right now. Yeah, so let's say n is the length of XS. Then we say that L is, well, actually we can use something called split at, which is a function that you give an integer where to split, and then you give an a list of A, and then it will split the list for you. So we just want to say that left right is equals split at, and then we give it the integer first, which is n, but not just n, it's n div 2, which is the list we want to split, which is XS. There we go. And then we can just write here, it's a join of L and R. Trivially easy. Let's see if I didn't fuck up some Grow. Okay, so let's see. They use an unfold, and then they have again they use the lambda case, where I just use a function. Either one works fine. And then they say that it is, this is their first case, and then here they use a let statement instead of a where, and they write, yeah, they div it here and then then just put the number here, but that's the same, you know, and then in join LR. Yeah, okay. One of the reasons I always do it like this, because it's easier to follow, especially since you put the type here, kind of forces you to think before you type, which I think is in in functional programming, if you have a type, the function is very close. So make tree an instance of the type class. Functor define map using fold. Fmap using fold. Yeah, I don't know why you would do that though. But we do. So yeah. Instance functor for tree. Now keep in mind that tree only has its recursive, or it doesn't have its constructor, or its type only has one argument, type argument, which means that this is the only type argument that we leave out, which means we also know what we're going to do the function on. Now we have the fmap. If you want for yourself, I think it might be good practice to implement well, actually, let's do that. I think we have time here. So it would look something like this, right? Single x is single of fx, and then the fmap on f for the join of LR is the join of the fmap of f on L and the fmap of f on R. Okay? But we're not allowed to use that. We have to do something like this. You are the tree, and you are the fold. All right. So let's go back to the type fold, which is right here. So this is fine, right? So actually, because this is the last argument that we have to give to the fold, let's remove it. But f we will need, of course, because we're going to have to use that in our G or our labdap, if you prefer that. So, G. I'm sure you know where this is going by now. So, the type of G. The type of G is actually not that interesting, because we already have it 17 lines up. Here. Let's copy that. Let's go 17 lines down and paste it. There we go. It's indented properly. That's it. Now keep in mind, of course, that the integer will be it won't be an integer anymore, but it's very similar. So an A, and then here we also have, well, this is a B, right? Given the type of F, and then here it's a B as well. Is it true? No, it's not. Because keep in mind that the result we want to have here, this A, is a tree, so the recursive tree again. Alright? So what will happen is that the fold will convert our tree into our non-recursive tree, and then we do our operations on that, and then we construct a tree again. So that's pretty cool. I kind of like that, actually. So this is a tree of B. There we go. I got interrupted again. Anyway, I think it's also useful to get the to write down the type of fmap, just to make it more clear as to what we're doing. Although this is something you should know by now. Oh, that's not how you comment it. It makes it a bit more obvious as to why I write tree of B here, because the intermediate results is, of course, I should write these though, shouldn't I? Is of course the what you want as a final result is also tree of B, so that's why I wrote it like this. It's good to remember that. So, what do we do? In case of a single of x, we write, well, we have to return a normal tree, so we write a single of fx. Sorry, I have to drink something. And then for the join, it's a simple matter of reconstructing it just with a normal join. There we go. yeah, I think that's it actually. Let's take a look. Oh, that was way too far. Map asphalt. Why didn't they just use fmap? That's a bit weird. Okay. uh, yeah. Yeah, no, this looks identical, right? Cool. Right. Again, make tree. Oh no, damn! I scrolled too far. Go up. Ah, right. Again, make tree an instance of type class function to define fmap using unfold. So it's just the same as we did here, but we have to use unfold. So let's actually copy. Oh no. Copy this. Paste it. And then put in here. Cool. And then we put where again. And then we put, no, not another where, put G here. Then we'll scroll up to the type of unfold again. And then we get the type. Okay, so unfold, we know that it produces a rec of F, which is our tree, right? Which means that we know okay, so the unfold is the opposite of fold, right? So where we had previously, we would produce a tree of A. What we'll do here is we take a tree of A and produce a non-recursive tree of A. Okay, so here we take a tree of A, and then we produce a tree of B and tree of A. So the reason it's B is because we have to produce, some B anyway, right? So we can't just always live in this A world. At some point it has to be a B, but this tree of A was set, and also this B is kind of like the result after, we are doing an operation that is on the singleton leaves, and we know that we need to apply the function on the singleton leaves, or just the leaves, not the singleton leaves. That doesn't make any sense. So it has to be B, right? At least that's my reasoning. So otherwise there's no other way to get a B. We have to produce a B in this function, which we also know that this B has to be on the leaves, right? So this is the only place it could be. So with that, we have two pattern matches again, like always, and this is the single of f of x, and then the g of the join is the trivial one, which is just the join of L and R. Let's check if this is correct. Whoa, I'm going way too far down. This is correctness. Here it is. If we take a single of x, then we produce a single of fx. If we take a join, we just produce a join. Alright, that's it. Nice.